This video introduces our paper Discontinuity-preserving normal integration with auxiliary edges. Our study focuses on normal integration, which is a process used to estimate the depth of a surface from its normal map. The primary goal is to convert the normal values, which are perpendicular to the surface gradients, into accurate depth values through integration. Integrating the gradient directly can ideally provide the desired surface, but this smooth surface assumption often fails in real-world scenarios, especially at occlusion boundaries. These boundaries cause distortions, and ignoring them leads to significant errors, as seen in the head part of the image where discontinuities occur. Thus, it's crucial to consider not only the surface gradient but also the depth jump between adjacent points, denoted as G'. Previous works have approached this problem in various ways. Naive methods assume continuity across all adjacent pixels, solving it like a Poisson equation. This leads to severe distortions since only the gradient G' is considered. Other advanced methods attempt to manage the errors sparsely by optimizing the discontinuity with techniques like L1 gradient minimization and bilateral weighting. Our key idea is to explicitly separate the surface gradient and the depth jump using auxiliary edges. By inserting these edges, we create a quadrilateral per pixel. In this model, the blue part follows the given normal, while the pink part represents the depth jump. This separation allows for more accurate modeling of the surface and its discontinuities. We developed an energy function based on our new discretization approach. We assume that G' is almost zero everywhere, minimizing its L0 norm. The data term ensures that the blue part matches the given gradient, while the pink part follows the depth jump. Since directly solving the L0 norm is challenging, we approximate the minimization using an iteratively reweighted least squares. This approach is commonly employed to achieve sparse solutions, making it suitable for our needs. Optimization proceeds iteratively. In each iteration, we solve a weighted least squares problem and update the weights. However, IRLS alone does not guarantee a global solution for L0. So we incorporated additional strategies. One such strategy involves directly manipulating G'. After computing the depth solution at each iteration, we calculate intermediate G' values and allow them to persist in subsequent iterations. We update these values only if they are larger than their neighboring values. To avoid local minima, we adjust the weight of the discontinuity energy in a manner similar to cosine annealing. When the weight is small, pixels move relatively freely, allowing G' to form. As the weight increases, pixels adhere closely together, reducing the risk of local minima. This visualization shows the evolution of G' over iterations. Bright areas indicate large G' values. As the iterations progress, G' becomes sparse and focuses only on necessary regions, demonstrating the effectiveness of our method. Our ablation study highlights the importance of each component in escaping local minima. Each component of our method, from reweighting to gradient filtering, contributes significantly to the final result. For complex shapes, the two-pass update shows substantial improvement. We compared our method with previous works using the Diligent dataset. Our method achieved higher scores quantitatively and preserved finer details qualitatively. Here are the results on a human model, demonstrating clear improvements in discontinuity preservation compared to previous methods. Another example with the T-Human 2.0 dataset further illustrates the effectiveness of our method in various scenarios. To summarize, our novel discretization method explicitly models sparse gradient magnitudes for occlusion boundaries, improving the integration process. However, our method does have limitations, such as difficulty in producing accurate multiple offsets for surface islands. Thank you.